Welcome to part 4 of my video series, Covariant Compactification, Progress Towards a Theory of Everything Fundamental. If you haven't yet watched parts 1, 2 and 3, you might want to do so before watching this. This talk is pitched at active physics researchers. However, there's plenty of material aimed at non-specialists on my website, Warped and Broken. If you'd like to support this physics research, you can do so by subscribing to my page on Patreon. There are currently 3 levels of subscription. The first level costs less each month than a cup of coffee or pint of beer in many cafes and bars, in UK currency just £4 plus VAT. With the second, at £15 per month plus sales tax, there's an option to be named on videos such as these. The most exclusive, at £100 per month plus tax, includes an option to be in a monthly group call with me and other patrons in this tier. My Patreon page includes both posts which are accessible to the general public and ones aimed at physics students and researchers. My ResearchGate page provides access to my various academic outputs. This is the 4th of a 5-part series. I'll start with a quick recap of what we covered in parts 1, 2 and 3. In part 1, the first 5 substantive slides of the video described the scientific motivation for the program of research which became covariant compactification. I stated in these slides that I'm aiming to explain all fields and matter in terms of spacetime geometry. I then moved on to the conceptual structure within which the content of the remaining videos of this series would fit. This involved finding harmonics on compact spaces and the quantum numbers they naturally have. In this conceptual structure, quantization is not taken as being imposed by hand, but instead it emerges naturally from the analysis. The second video in the series started by looking at diffeomorphisms on spacetime, tangent fields and their covariant derivatives. It considered product spacetimes and how, on these, certain components of the spin connection can be identified with gauge fields, and I provided 2 examples of this. 2 field equations were derived for the tangent fields, and I looked briefly at cosmological implications. In the third video, we started studying the harmonics on the background spacetime and how these could describe matter fields. We looked at the 2 factor spaces separately, S3 and S6. We found that there was a multiplet of harmonics on the S3 space, which under rotational diffeomorphisms on the space had the quantum numbers of an SO4 spinor. Similarly, there was a multiplet of harmonics on the S6 space, which under rotations around the origin had the quantum numbers of an SO6 spinor. We showed that the product of the spinor, that the spinors of the product of these groups accounted for all of the states in a single generation of fermions, including right-handed neutrinos. These sterile neutrinos were invariant under precisely the gauge group of the standard model. We therefore proposed that they formed a background field, perturbations of which would be quarks, charged leptons, and left-handed neutrinos. In this video, we turn to look at field dynamics, studying this in the flat space limit. In doing this, we will start to see how the uncertainty rules of quantum theory can emerge. We begin by focusing on eigenfunctions of the translation operator and their wave numbers, and how they form a basis for decomposing more general wave functions. We will describe how signal processing research revealed an uncertainty relation between wave number and position for superpositions of the eigenfunctions. We look at concepts of modulating these eigenfunctions, both in 1 dimension and in 4. In the second section, we use classical electromagnetic theory as an analogy for defining the energy and momentum carried by a wave and show that their densities form a tensor field. We'll quote a specific form of density tensor field for monochromatic waves. We'll then integrate these to find that the energy momentum itself forms a 4-vector associated with the whole of a spatial volume. The uncertainty relation can then be recast in these terms. 2 of these topics will be considered further in Part 5. Firstly, we'll look at how the uncertainty relation plays out in de Sitter spacetime. Secondly, we'll generalize the expression for the energy momentum density of monochromatic waves to fit superpositions of them, and use this to derive Einstein's field equation. In the third section of this video, we look at pure gauge U1 transformations. We show that local changes of phase represent a local change of basis on the Hilbert space of Fourier modes, corresponding to a modulation of waves in that neighborhood. This means that the momentum of such a wave changes, so that such transformations are manifested as a force, quantified by a gauge potential. We'll see that although the potentials may have zero field strength, they still have a measurable effect on the waves, as happens with inertial forces and in the Aharonov-Bohm effect. Again, this analysis will be extended in Part 5, where we consider the geometric meaning of local SU4 transformations, both with zero and non-zero field strength. In this section, we'll look at wave-like configurations of fields, first in 1 dimension, then in 4. We'll consider ways to analyze these waveforms, which again take values in a Hilbert space. We'll start by looking at the eigenfunctions and eigenvalues of the translation operator and how Fourier decomposition of a waveform provides an uncertainty relation. We'll then look at modulating these eigenfunctions and see that this is equivalent to changing the basis on the Hilbert space. In flat 4D spacetime, we'll see that any waveform which is an eigenfunction of all 4 Cartesian differential operators obeys a wave equation. To start with, consider field configurations on a 1-dimensional space. We'll choose a parameter eta on this space and consider a function phi of eta. Now map each point on the space to one such that its value of eta is increased by an amount delta eta. This is a simple translation. Just as for the SO4 transformations, these can induce a transformation of the field by dragging it along. Again, we can tailor-expand the new configuration around the old one. The generator of this transformation is simply the derivative operator. We can express the eigenfunctions of this operator in either of these forms, either with a complex leading coefficient or with a real coefficient and an added phase alpha. For these, we find that the dragging action multiplies it by a complex number. If lambda takes one of this series of values, then phi is invariant, that is, symmetric under translations through delta eta. Thus, for each displacement delta eta, we have an infinite series of eigenvalues, and corresponding to each, there is a function which is symmetric under translations through that interval. Now, it may happen that a field configuration is localized within a range of eta. That is, its value is negligible outside this range. For simplicity, we'll use a symmetric range from -L to L and assume it to be 0 at these points as well. There are an infinite number of ways we can specify this field configuration. There are 2 ways that are particularly of use to us. The first is using specific eigenfunctions of the derivative operator. For an eigenfunction of the derivative operator to be periodic over this interval, it must be symmetric under a translation through 2L. This requires lambda to be an integer multiple of pi over L. Thus, n is the number of wavelengths that fit into the interval. We can regard the periodic eigenfunctions as states in a complex Hilbert space equipped with an inner product as shown here. Our localized configuration phi is then an element of this Hilbert space. Within this inner product, we define an infinite set of orthonormal basis states. Note that although we're using Dirac's bracket notation here, there's no requirement for these to represent quantum particle wave functions. The analysis is so general that it could, for example, be used for complex combinations of water waves in a canal. Nonetheless, we'll term the states with a specific value of n monochromatic. We can consider phi as part of an infinite waveform, capital Phi, with period 2L. Then, if our localized configuration is continuous over the range, with a finite number of maxima and minima within the range, we can express the extended waveform as a complex linear sum of the basis states, a Fourier series. As usual, the eigenvalue of a monochromatic wave is termed its wave number, the number of wavelengths that fits into an interval of minus pi to pi. This simplifies the exponentials. For any phi, one can calculate the standard deviation of phi, which we call sigma eta, and the standard deviation of the amplitudes of the monochromatic waves in its Fourier series, which we call sigma n. This can be rewritten as a spread in wave number, sigma k. For a Gaussian waveform, the product of sigma k and sigma eta is 1. In general, the product is at least 1. This is also valid in the limit of infinite period, in which case the Fourier series becomes a Fourier transform. Proof of this was given in a 1946 paper on signal processing by Gabor, in which he considered the question of the minimum number of data needed to reproduce a given waveform. The second way of specifying the field configuration was developed by Wille, drawing on Gabor's work and on work by Carson and Fry. It's essentially a quantification of the concept of frequency modulation. We start by expressing a normalized monochromatic wave in terms of a dimensionless phase. This is linear in the parameter eta, so the wave number can be expressed in either of these forms. Modulating the wave number changes the phase, creating a waveform that no longer has a single static wave number. However, we can define an instantaneous wave number, which varies with the parameter. Defining it as the differential of the phase ensures it has the appropriate units. In Wille's work, the parameter was time, so the instantaneous wave number is an instantaneous frequency. We can easily find a relation which expresses this in terms of the full waveform. The interval may be parameterized in other ways. If two parameters eta and eta primed are linearly related, they share a common basis. If they are not, then the phase of psi n is not linear in eta primed, and d by the eta primed has a new set of eigenfunctions, forming a new basis for the Hilbert space. This gives us a new understanding of frequency modulation as a change of basis on the Hilbert space. Take a monochromatic wave in the eta basis, then apply a modulation. It's then easy to find a parameter for which this is an eigenfunction of the corresponding differential operator. We just divide the phase by any valid value of k primed. Note that this includes situations in which the modulation dies away towards the end of the interval. In this case, the period of the waveform tends to that of the carrier wave in these limits, so the parameter eta primed converges with eta towards the boundaries. This will be of particular interest when we come to look at central potentials. Let's now go up to four-dimensional Minkowski spacetime. In this case, we can consider field configurations that are localized within ranges in each of the 4 dimensions. As the differential operators with respect to the Minkowski coordinates all commute, we can find simultaneous eigenfunctions of all of them. Those with appropriate values of the 4 wave numbers, knx, kny, knz, and ν, can be used in the Fourier analysis of field configurations within our specified region of spacetime. These wave numbers are partial derivatives of the phase, known in this case as the eikenal. As the first derivatives of an eigenfunction are proportional to that eigenfunction, the same is also true of the second derivatives. The proportionalities are negative products of the wave numbers. Eigenfunctions also have the following properties. If n nu is 0, the eigenfunction is stationary. An eigenfunction only satisfies Laplace's equation if all 3 spatial wave numbers are 0. This means that at any moment in time it's constant over space. All eigenfunctions satisfy a wave equation where the velocity of propagation has this form. If we now define a quantity k0 as being the ratio between the velocity of propagation and the speed of light in vacuum, we find that it's related to the spatial wave numbers by this equation. We can therefore consider these 4 quantities to be the Lorentz components of an object, which is null when the wave propagates at the speed of light. We'll see shortly that this object isn't, as might be expected, a true 4 vector. In 4 dimensions, we can consider waveforms for which the wave number is not constant using the same methods as for the 1-dimensional case. The eikenal is now a generic function of the coordinates. The wave number components are still given by its partial derivatives and are related to phi itself using an expression similar to our previous one for instantaneous wave number. Consequently, the eikenal can be expressed as a line integral of the wave number, and capital Phi is its exponential. In this section, we recap how energy and momentum densities are derived from monochromatic electromagnetic waves and the resulting form of the energy momentum density tensor. We adopt this form as a definition for the tensor for a monochromatic wave of any field. This allows us to show that the energy and momentum within a given volume forms a 4 vector which is proportional to the wave number. This analysis is based on the book The Classical Theory of Fields by Landau and Lifshitz. Combining this result with the one from the last section on Fourier analysis, we get uncertainty relations for momentum and position and for energy and time, which take the same form as those of Heisenberg. In classical electromagnetism, we can consider a monochromatic wave incident on a pattern of charges. We can use Maxwell's equations to calculate the energy and momentum transferred per unit volume. This is done in various textbooks, such as Duffin and Wrights, Milford and Christie. Then, invoking the conservation laws for these quantities, we find that these are the energy and momentum densities for the wave. In relativity, these energy and momentum densities form part of the energy-momentum density tensor. This tensor takes this form. We shall take this to be the definition of the energy and momentum density tensor for any monochromatic wave in flat spacetime. Collectively denoting the energy and momentum densities by curly p mu, we find that this is always proportional to k mu. That is, not only does the momentum density vector pi point in the same direction as the wave vector ki, but also the ratio between them is the same as the ratio between curly p naught and k naught. We call this ratio curly h. We can see it as a conversion factor between wave number and momentum density. At any given moment in time, the energy and momentum in a given volume of space V can then be found by integrating over V. If there is no net flow of energy or momentum out of this space, and the waves are non-interacting, then these are conserved quantities. We will therefore drop this evaluation at t equals t naught from this point on. The conversion factor curly h survives the integration, while k mu is constant for a monochromatic wave, so we find that p is proportional to k with the same proportionality for all four components. This is a true 4 vector, but it isn't a field. In the same way that a point vector takes its value at a specified point, this takes its value for a specified volume. The volume, meanwhile, isn't invariant under changes of coordinate system. Consequently, k mu doesn't transform as a 4 vector. Our relation between p and k means that anywhere k mu appears, we can replace it by p mu for a volume divided by curly h times that volume. We now recall Bohr's result for spreads in k and eta in a Fourier decomposition. The proportionality means that we can express the former as a spread in momentum or energy, while the latter is a spread in a space or time coordinate. This gives us uncertainty relations with the same form as Heisenberg's for momentum and for energy. In this section, we look at what happens if a waveform is multiplied by a complex field of unit modulus. We see that it acts as a force which modulates the waveform's frequency and changes the momentum carried by a volume of the waveform. The change in the momentum depends on the gauge field's potential, not its field strength. This is consistent with both the effect of inertial forces in Newtonian theory and the Aharonov-Bohm effect. Multiplying a waveform by a complex number of unit modulus, that is an element of U1, shifts its phase. Note that if we have a D-component spinner, the kind of objects we looked at in part 3, we can have up to D independent mutually commuting U1 transformation groups acting on it. Indeed, we can take a set of D such transformation groups to be generated by diagonal matrices. The phase shifts resulting from these groups depend on the quantum numbers for each of the components. In part 3, we encountered several such diagonal U1 groups. These included the third components of the left and right SU2 groups, which act on the two spinors of SO4 as shown here. They also included the diagonal U1 subgroups of color SU3. I've just shown one of the pair here to save space. If we combine the third generator of the SU2 left group with the weak hypercharge generator using the Gell-Mann-Nishijima formula, we can also get the generator of the electromagnetic U1. This acts as shown here. The factors of the SO4 multiplet combine with those for the SU4 multiplet to ensure that up quarks, down quarks, neutrinos, and charged leptons all have the appropriate electric charge. Returning to our single component waveforms, we can apply the element of U1 to each of the Fourier modes. Each mode has a conjugate which undergoes the inverse transformation. While the notations in these equations assumes a single spatial or time parameter, these general features are just as valid in 4 dimensions as in 1 dimension, and for coordinate-dependent U1 transformations. By comparing the phase shifts at 2 nearby points, P and P primed, and Taylor expanding the shift at P primed around that at P, we can find how the instantaneous four-wavenumber is transformed. It's shifted by this Marat-Cartan type term. From our previous expressions for the four momentum and its density, we can find their variations under a local unitary transformation. This means that a phase shift that varies along the wave's direction of travel changes the wave's momentum as it moves. This can be interpreted as a force acting on the wave. We may ascribe a potential to this force, which will denote A mu. Note that a potential with this Marat-Cartan type form has zero field strength. However, as we'll see, this still has physical measurable implications. When multiplied by a charge carried by the wave, this gives the change in the wave's momentum resulting from the phase shift. This shift in momentum is precisely the effect of an electromagnetic field on the momentum eigenvalue in quantum mechanics. Consider the case where A mu is a central potential, one in which the potential depends only on the distance from the center. For a wave propagating through it, the four-wave number will shift monotonically as the distance from the center reduces. At close ranges, the change in the wave number resulting from the potential will be much larger than the initial wave number. If the initial wave number and the U1 potential are oppositely aligned, this could reverse the direction of the wave number and hugely increase its magnitude. If they are not, the effective change to the wave number could still swamp the original signal. Thus, at close ranges, the wave bunches up, oscillating rapidly. Essentially, the U1 field is modulating the wave's frequency. Note that this idea of a potential causing shift to frequency and wave number is consistent with what we know about gravity. A gravitational field can cause an electromagnetic wave to experience a frequency shift. Indeed, a gravitational wave will cause alternating contraction and dilation of spacetime, which would result in alternating red and blue shifting of electromagnetic waves. This will happen in our case of a U1 potential too. If a wave carrying a charge interacts with an incident wave of the U1 gauge symmetry, it will cause alternating dilations and contractions in the frequency and spatial wave number of the charged wave. It's worth thinking more about the momentum carried by a wave being shifted by a gauge transformation. This idea of a gauge-dependent momentum may seem a strange one. But the notion that a potential with zero field strength can affect physically observable quantities is certainly not a new one. Firstly, in Newtonian physics, if we change the reference frame by accelerating, this results in the appearance of inertial forces. The effects of these are most certainly felt by the observer. This persists into general relativity, which essentially shows that inertial forces can be viewed as a gravitational potential, or more properly, a connection, with zero field strength. Secondly, this idea is behind the Aharonov-Bohm effect, which we will turn to now. The original Aharonov-Bohm effect, as is well known, is one in which the wave function of a charged quantum particle is affected by an electromagnetic potential in a measurable way. However, variants on this situation have now been proposed and experimentally tested: the effect of a gravitational potential on a wave function and the effect of a vortex on a water wave. We'll summarize the electromagnetic effect first. In the classic setup, a solenoid has an electromagnetic potential circulating around it and an angular potential within it. The functional forms of these mean that the field strength is zero everywhere outside the solenoid, while within it, field strength has a magnetic component pointing along the coil. Source emits electrons towards a screen with two slits. This splits the electron's wave function in two. These waves then pass through the region surrounding the solenoid. In this region, the potential affects the wave function in the way we have seen. This is often described in textbooks, for example, Quantum Field Theory by Ryder, simply as shifting the phase of the wave. With the analysis we've been through, we can be more precise and say that the potential is actually modulating the frequency of the wave. On one side of the solenoid, the potential reinforces the wave number, increasing it in the direction it's already pointing in, while on the other side, the change in the wave number is in the opposite direction. The waves then recombine at a screen, and in some places on it, the wave functions from the two paths interfere constructively, in some places destructively, resulting in interference bands. The phase shift caused by the potential by the time the electrons reach the screen results in this interference pattern being shifted along the screen, compared with what would otherwise be observed in the absence of the field. Very soon after Aharonov and Bohm published this theoretical prediction, the experiment was carried out using a magnetic whisker. This produced the predicted effect. There was some leakage of the magnetic field from the solenoid, but later experiments without such leakage have also verified the predictions. In 2022, a team led by Mark Kasevich performed an experiment to test whether a gravitational potential could also shift the interference pattern for a quantum particle. In this experiment, lasers were used to split the wave function of rubidium atoms. The resulting wave functions took different paths around a 1 kilogram mass of tungsten. The gravitational field of the tungsten again acted differently on different paths. When the two parts of the atom's wave function recombined, it was found that the interference pattern was shifted by the gravitational field. As I understand it, this was not looking at the effect of a potential with zero field strength. That would be done by causing a linear acceleration. This was an actual gravitational field, that is, a non-zero curvature of spacetime. Nonetheless, it verifies that a differential phase shift can be caused by a gravitational potential. An analogous effect has also been predicted and verified for water waves. In this case, the setup is a tank of water in which a dipper causes waves to move along the tank. A hole in the bottom of the tank causes a vortex in the surrounding region. A team led by Michael Berry predicted that this would cause waves moving through the vortex on one side of the hole to bunch up, and those on the other side to space out. This would result in dislocations in the wavefronts characterized by a phase shift. They carried out the experiment, lighting the tank from below, photographing the images falling on a screen above the tank, and verified their predictions. We finished this video by drawing out some key conclusions from it, which we can take into the final part of the series. The three Aharonov-Bohm experiments show that the action of a potential on a wave, changing its frequency or wave number, is a very general one. It applies to both electromagnetic and gravitational potentials. Furthermore, the wave does not have to be a quantum mechanical one. It could equally be a classical one. Indeed, nowhere in this analysis have we assumed the waveforms we are looking at to be quantum wave functions. All of this analysis would be just as applicable to, for example, complex combinations of waves on water. The generality of it will allow us to apply it to wave-like configurations of the field root mod G that we've considered in previous parts of this series. Nonetheless, we've ended up with uncertainty relations between the energy momentum carried by a wave packet and its spread in spacetime. We've also ended up finding a definition for the energy momentum density tensor of a momentum eigenstate, which is proportional to the symmetric tensor created from its four-wavenumber.